Welcome. Today we're going to go through my rocket code. This is the code that has run on most of my rocket launches with a few tweaks between rocket launches. And yeah, I put it on GitHub. It's out there on GitHub. You can get it. You can go to this link up here, Cygnus X1 software right here, or you can go in the description of the video and yeah, and you can check out this code yourself. And but today in this video, I'm just gonna go through an explanation of sort of how the code works and what each of the settings are and what are the states of the code and sort of yeah, basically how it works and stuff. I wrote this. You can see the last time I changed these things were like last year. I just haven't been pushing updates to it that often, but it's still fairly sort of, it still works, and there's a lot of sort of settings and stuff. So let's get to it. So all you can do is you can clone the repo, or you can download the zip file, which will have all these files in here. But I'm gonna open it up in VS Code right here. You can see here I have all of the files here. So there's a lot of files here that don't really matter. So for example, this test folder, this is when I was like testing random stuff, and there's a lot of different CPP files and .h files and that are not being used anymore, but I would use these for, like, let's say here I wrote a little thing, or I found a little thing to do a full chip erase for Flash when I was testing. You know, so this stuff is important. So in this test folder, you can ignore that. When you compile all this and build it and upload it to a rocket, you know, don't have this test folder. It's only going to compile what's in the source folder. So this is using platform IO. So you can see the little alien head here, and this is platform IO. And I have a bunch of little projects with platform IO. And I use this to upload the code and, you know, upload the code and, you know, build it and all that stuff. So I can use VS Code rather than having to use, yeah, and I've got a lot of other projects with that. But if we go back to the full file, so in source, this is where all the important stuff is. So each of the sort of, you know, a lot of these file names are self-explanatory. So, you know, each of these files sort of handles a different component of the rocket. So things like handling the buzzer, things like handling Bluetooth low energy, so that's just the Bluetooth section, things just handling the altimeter, you know, GPS, navigation handling, a quaternion sort of library that sort of helps me with quaternions, a telemetry sort of handler that, you know, hooks up with the Bluetooth and gives me telemetry to my phone. And so the main one is this main.cpp here, obviously. But we also have a few folders here, so I kind of divided a few things up into a few of these folders, because something like the Bluetooth stuff, it's got a lot of stuff that I didn't write, and this is all, a lot of these things are from another library that helped get that Bluetooth, Bluetooth sort of working for me, and so I just stuff them in a Bluetooth folder, and it's got all the things I need. Digital I/O, I do not remember what this is anymore. EUI, so EUI is a library. It's called Electric UI, and we can do a little shout out here for Electric UI. Electric UI, basically, I was using this to hook up my rocket over a serial connection to this kind of, to a sort of like an interface where Electric UI would sort of take a bunch of data from my rocket and put it into this interface here, you know, a custom one that I made, and then show like a dashboard of live data. So while I was testing it, I can see the graphs of things like, you know, is the altitude changing correctly? Are my gyros, you know, doing what they should do? Things like that. So this has been super valuable. And yeah, shout out to Electric UI and Mike Dax. He's like a guy in the BPS space, or he was, maybe he still is, I don't know, a guy in the BPS space channel. yeah, so let's go back to the code here. So EUI, it's a great library. There's a bunch of little things you need to add and stuff, and I also added a few things, and it's great for testing, especially testing on the ground. This is libraries, so this is things like controlling the little NeoPixel LED that I have on the little computer. So I use this Adafruit library, the BMI 088, so the altimeter. I think this is the altimeter. No, I forgot these. I think this is the gyro and the IMU, right? So this is the IMU library. This is for these MS5607. That's the altimeter library, and then there's a tiny GPS library for when I tried to get GPS to work. And I made a few changes to the altimeter, to this specific altimeter library, which I have in another video, where basically it's non-blocking. Basically, the original library is blocking, so it has an actual delay of 3 milliseconds, which we don't want in our flight computer software. We want this non-blocking. So there's sort of a coding thing that I did where it goes through different states and it checks if it every time it's ready to sort of go into the loop again, it checks, hey, are we in this state, and has this time passed, then do the next thing. And so rather than waiting for the 3 milliseconds to in the code and blocking it, we just call it about every time we are going through the loop and see if 3 milliseconds has passed. But anyways, yeah, so that's another video. So that's libraries. Other main files. Oh yeah, this is when I was like testing a bunch of sort of a bunch of different programs that I wanted to put onto the flight computer to test a bunch of things, and I would, originally I would call them main.cpp because that would be the program, but then when I didn't need to use it at the time, I would just put this into the title of the thing and then .temp. And this is, they're files that are smaller files that do, that are basically main.cpp files, but just renamed. And these are not compiled or anything. These are just for like, historical use later. Then there's SD card, which has a lot of files here. And these are things to deal with the SD card plus the SPI flash. Unfortunately, I don't really remember exactly how all this went together and how all this works, but basically this helps this library that I use for the SD card and the SPI flash chip. Basically helps those communicate with the flight computer, and so a lot of these have been taken from a few places. Yeah, and then the rest is sort of the flight computer code. So let's start with main.cpp. So the way main.cpp, so the way the rocket works at the beginning is it does a bunch of setup, right? So this is just a bunch of variables that we need to keep track of and some functions. But here in void setup, this is where it does all the initialization. So right when I turn on that switch on the rocket to power it up, we've got an init buzzer function here, which just beeps the buzzer twice, like beep beep, and just to let me know, hey, I'm alive. And then we have a serial begin here, 2 serial begins. I don't remember exactly why we have 2, but I keep them in here. I think it was just for debugging and stuff, but whatever. Then there's a handle dump data. So this is a special function that I made for if the data of the rocket did not, basically if the data of the rocket did not did not upload properly at the end of the flight, it would still be in the flash chip. So what this does is it basically says, hey, if there's a little config variable here that I can configure to the code and say, well, if we are in dump mode, basically just dump the data to the SD card, and then we buzz complete, right? So we just stay there. And this basically makes it so that at the end of the flight, so the way the flash works is at the end of the flight, the flash gets or I think at the beginning, yeah, in init flash, the flash chip gets erased, and then the flight the flight goes on, the rocket lands, and it writes all the flash data to the SD card. It does not delete the flash data yet. it deletes the flash data on the next time it the startup. So what this does is, if I see that the SD card got corrupted data or it didn't transfer properly or whatever, what I can do is upload some new code to it with this is dump mode true, and this handle dump data will just dump the previous flash chip's data onto an SD card, and then I can just read it from there, and it's just going to stay in this infinite while loop buzzing to say it's done, and it's not going to erase it until I remove this is dump mode and I make this false, and then it starts the setup again. So that's handle dump data. Then there's go to state. So basically I have this function that says go to state, and inside of it, it's just, I have this data.cvp.h sort of file here that worries about data, all the data stuff, and so one of these things is go to state, and all it is just saying, hey, the data.state struct, the data.state variable should just be the state that I tell it to go to. And then float state, I think is just for tracking, because I think the enums, something enums, I don't know. But I guess at this point it's a good idea to go through this data function, because a lot of this data stuff is very important. So, with this rocket, I need to track I need to save a lot of data, right? So the flash chip, while the rocket's flying, is saving all of this data every, at a specific period, or sorry, at a specific interval, right? So I think based on this data sample rate, so this is every 200 milliseconds or something, and then how much time? 45 seconds worth into the flight, or starting at the beginning of the flight. And so basically we have to log a lot of data. We have things like altitude data, we have common filter data, we have gyroscope, accelerometer data, we have a lot of things. And so the actual data structure that holds all that data is in this data.h file here. So you can see here we have a struct of data, and we have all these variables, right? So milliseconds is how much time has gone through, like since I pressed launch. Accelerometers, world accelerations. So this is like, accelerations that are in reference to like the world, up and down, left, right coordinates, like the beginning sort of initial state coordinates of the rocket. Then there's gyroscopes, yaw, pitch, roll, altitude, a bias altitude. So this is what I calculate this at the beginning before launch. Whatever command, the Bluetooth something, I don't know. Servo Centers. So I have a thing in the app where I can set the center points of my servos, and then it saves it to the flash chip. And the next time I turn it off and on again, it reads those servo centers and make sure that those are the centers. And every time we tell the servos to move somewhere, we offset it by that center point. We have loop time, so this is just keeping track how much time has gone between each full sort of software loop or control loop, I guess. We've got state, and we have F state, so this is where it comes in, this what state we're in. So F state is a number between 0 and 6 or something like that, depending on how many states we have. Then there's Kalman filter stuff. So X is sort of the vertical up and down. X is sort of the vertical up and down axis. So I don't know what it's called. Yeah, basically the vertical up and down rocket axis, right? From the tip of the rocket nose to the engine. You draw a line, that's the x-axis. And so we have a common filter basically getting altitude data from both the accelerometer and the barometer. So it's mixing those two together to get a more accurate altitude. And so this is Kalman X position, velocity, acceleration, and then position p-value, velocity p-value, acceleration p-value. P, I think, is like, I don't remember exactly anymore, but it's like variance, I think, or something to do with that. I don't really look at this too much anymore. K1 and K2, so those are Kalman gains. And then Kalman inno, which is Kalman innovation, which is another sort of common variable. Then there's my servo Z and Y. So this is what are the commands that are being written to the servos, or that the servos are being told to do. Then there's my PID gains, so my PID gains for the Y servo, and my PID gains for the Z servo. And then there's my PID errors in Y and Z. And then yaw bias and pitch bias. So that is, I think, just the yaw and pitch that the rocket originally starts at compared to the Earth coordinates. So I make sure that, so I use the accelerometer for that. Battery voltage, that's self-explanatory. And then for GPS stuff like latitude, longitude, the altitude GPS tells me the altitude bias from the GPS, how many satellites there are, my HDOP. Then there's world world acceleration XYZ biases. I don't know if I use those. Maybe I do. I think I just use those to calculate world XYZ. Then there's accelerometer magnitude. So I like to track this. It's just basically the XYZ accelerations, all of them squared and added a sum of the square root of the sum of the squares. And this is just the magnitude because I use it in certain places. Then there's Pyro 1 continuity. So this is just keeping track of the continuity of the Pyro. And then there's PID, the del T. So this is for the derivative term, I think. Or no, this is the difference in time that I use for the derivative term. I don't really know if I need it anymore, but it was there for like error checking and stuff. So yeah, that's all the data I log. And this is logged every 200 milliseconds or something, apparently. Or that's the sample rate. So no, sorry, not 200 milliseconds. If we go back, the sample rate is here. So that's 200 samples per second. So that's actually every 5 milliseconds it's logged. And basically we have some code here that basically worries about addresses and writing addresses and making sure that we go to the next address and stuff when we write to the next, all that stuff. It's kind of beyond my remembrance now at this point. Let's go back to main. So that was the data. So next is so we go to state. We say, hey, at the beginning, the first state will be initializing, which we'll worry about later after the setup function. Then we delay for 10 seconds. I don't remember exactly why. I think it was just to, I don't know, just give us some time to delay. Buzz startup. So now we have like another little buzzer sound, which is just another beep beep kind of thing. Buzz startup, you can see it's really just, there is like delays in here. So this is blocking. It just writes to the buzzer pin on and off, on and off. It's an analog write. So I think I messed up the buzzer. I didn't put it on a PWM pin or a proper PWM pin or something. And so the buzzer, it can't change the tone basically of the buzzer, so I can't make any fun music, which kind of sucks because that was the thing I wanted to do. But it can, it just does like one single frequency of tone, so which is kind of boring. But yeah, this one buzz startup goes beep beep, and then there's like buzz long, so there's like beep beep, and then different kind of buzz. So there's like a buzz complete where it does it 3 times just to sort of let you know what's happening. Then there's init flash. So init flash this is where the erasing happens. So we do flash begin. We read the TVC centers, which we basically, we read from the flash from the old TVC centers. We erase the whole chip, and then we write to the TVC centers. So right, because we don't want to erase the TVC center point values and not have them anymore. So we basically extract them, erase the chip, and then put them back into the chip and set the TVC centers properly. And then we do something like get max address, which basically just gets the address based on capacity of the chip, and it's used so that we don't overflow it or something. But I don't know if we need it, but. Then there's init Bluetooth. So there's a lot of things that happen when we're initializing Bluetooth, and this is part of like the BTLE CPP. And this is a lot of stuff that I don't know about. But then there's like init pins that I also haven't written. Yeah, this is something maybe I did. So I specifically like say what pins these are because it's a custom PCB that I made. So the pins for the Bluetooth go to specific places. Init PNIDs. So init PNIDs basically sets the the PNID values in the data struct to the ones that I have in the config file, which I'll get to soon. It sets the tuning, so it sets those values. It sets the output limits based on the servo range that I put in, and it sets the set point to whatever set point I put in. So it's gonna, obviously we want to go straight up. We say the set point should be 0, 0. Init parachute. This is where the parachute, what it does is it just writes to the servo a value, which I know from before, and what it does is the servo, that's where the servo engages the parachute sort of latch. So at this point, I hear the servo sort of turn on, and then it's fighting against the little parachute latch thing. So I push the parachute down, and it's spring loaded. So when I push it down, it clicks into place, and the servo holds it down, and it's ready to launch. And then there's, the parachute function is very simple. It's, hey, initialize it by causing, latching in, and then deploy the parachute by writing the deploy value, which is in this case 50. And I also have a thing where, hey, if I want to enable the parachute, which I most certainly do it in most flights, if it's true, then yeah, then deploy it. I think I had this here because if I was testing it, I didn't want it to deploy. So that's init parachute. Then we delay again. Then we do init nav. So initialize navigation, and this is the thing that takes the longest. So this initialize the altimeter, which basically first starts it up, and it gets the altitude bias. So it sort of takes a few. It looks like it takes 100 measurements here, and it averages them out so that we can get our zero altitude. Then there's accelerometer begin and gyro begin. And this is where we also zero the gyroscope. We get the gyro biases. And we zero the gyroscope, I guess, again. Don't know why we do it twice, but... I think we do it twice because getting the gyro biases takes a little while. And so we just want to zero the gyroscope again, which just basically sets the, it sets the values to 0 for while we're... because these need to be set to specific things for the whole quaternion calculation and all that stuff to happen. Then there's buzz fast, which is like a fast kind of beep beep. Delay again, buzz startups. We do another startup buzz. We delay again. We do it again. And then here, if we had electric UI enabled in the config, we initialize it as well. And then we initialize the servos. So initialize servos. I guess it's part of this. It's referencing the wrong. This is what's weird. It's referencing the wrong files. But init servos, if I look at where servo is, servo control. Yeah, init servos here. It basically attaches the servo pins for X and Y, the TVC servos, and then it writes the center values to those servos. And then we say, okay, this is for our data, this servo Y and Z is 0 at the beginning. And then there's init pyro. So init pyro is pretty important. We say if the config says that we're going to engage the pyro for this flight, which we almost always are, we're going to set the pin mode to an output, and we say, we basically check, this is where we check the continuity the first time. So we say, if this pyro pin detects that the voltage, the voltage value is less than 200, that means we have a continuity of 0, and because there's no voltage flowing or whatever, there's very little. And if it's above 200, we say, hey, there is continuity because we have a voltage coming through. And this is just for the beginning. Later we have a function where we constantly at the beginning do this checking every second to see if the continuity is if there is continuity or not, so that it can. So that in our app we can see our app will literally not let us press the launch button if there's no continuity. Then there's things like setting up some times, so for loop times and stuff, and then we say if we're in test mode, go to the test state, but for a flight we're not in test mode, so we're going to go to this idle state. So we got idle right here. Then there's the function for handle run nav, which I'll close for now. Handle write into flash, close for now. Some of these should be not here. And this is not I'm not a like professional C++ coder. Then there's a few more variables here, and here's the main sort of workhorse, this void loop, and it does a lot of things. Things like time things. So what was we want to track the time between loops and things. Then there's a bunch of things. So on each loop, so this loop runs constantly, right? It's just always running this loop function. When it finishes it, it goes back and starts from the top again. And so here we have things like handle run nav, so that will handle running the navigation. So if we go into that, this just looks like, okay, handle altimeter. So this is where, hey, this is where it gets the altitude and writes it into the data structure. Then we say if we have a nav timer, so if the timer has passed a certain nav rate, which is 5 milliseconds here, so if it's past 5 milliseconds, we're going to get the acceleration, get the yaw pitch roll. So this yaw pitch roll get does like a whole equation with quaternions. And then we say this also like we're doing this handle run nav. If we're in the idle state, then we're also getting a move like an average world XXL value so that we can continuously like update our bias. And then we predict based on, so this predict is from the common filter, so it does a predict step with the accelerometer. So while it's flying, it's doing this predict step. And if the PID status is true, so PID status is basically a flag or a variable, a Boolean that basically says, okay, do we start calculating the PID values now or not, right? So are we calculating PID values or are we not? And are we actually moving the motors? So during idle, we don't want to be calculating the PID values and stuff because there's no actuation available. There's no, the rocket isn't actually moving at all, and we can't affect its yaw pitch or yaw and pitch while it's on the pad. So we don't want to have the PID running at this point because it will start accumulating errors and the I gain will start to go really high, and the first time we turn on the rocket, the motor is going to already want to be trying to correct for it because it's been building up over time. So there's a point where when we detect there's a point where we turn on this PID when we launch the rocket. But what happens is, we feed it the pitch and yaw that we got. We compute both the PID values, and then we just, which basically moves the outputs of the pitch and yaw PIDs into this data.servo z and y values, and then we use those with the offset centers to move the servos, to move the z and y servos. And move z and y servo, all it is just says, hey, z servo write this value. I don't even know if I need this kind of function here, but whatever. And then we restart the nav timer here, right? So right after this is all done, we wait another 5 milliseconds and we restart it. It might be better to like have this like up here. So we restart the nav timer. So because what happens is when we restart it at the bottom, this might take 5 milliseconds, but then we restart and we're waiting another 5 milliseconds. So technically 10 milliseconds passes. But if we restart it up here, that starts the restart, and then once this is done, then it's not going to wait all that extra time. It's still just going to wait 5 milliseconds since this restart, but I'll just keep it here for now. Not a big deal, probably. And then we say if, what else here? Yeah, so if is there new altimeter data, which basically says, remember how we said this is non-blocking anymore? So we're basically saying, hey, if sometimes when we handle this run nav, this altimeter isn't actually giving us new data. It's just, running through the next state, update state of its sort of cycle of getting that data. And so here, if we can say, we check if there is new data, like if this run through of this function actually is one where we get new data, then we're going to get that altitude, and we're going to update the barometer the barometer part of the Kalman filter with that altitude. We don't want to be updating the barometer part of the Kalman filter with old altitude data. We're just updating it every time we get a new data point for it. Yeah, so that's really handle run nav. Get yaw pitch roll is kind of tricky. So yaw pitch roll here is a huge sort of function here. You'd want to read it on, read about it yourself and look into it. There's a lot of trial and error I had to go through with figuring out like what axes are the right axes for the yaw and pitch and things like that. And basically a lot of this stuff is quaternion math, basically converting the gyroscope values into a yaw pitch roll. You can see here, and then also this is bad coding practice, but also there's also a world AX, AY, AZ calculation going on as well. And then at some points I'm doing, I'm using the quaternion library here, but then I'm rotating it. Oh, sorry, I'm using the quaternion library here for this stuff, but over here I'm doing them manually. So it's really messy. But then here we do quat to Euler, which we give it this yaw pitch roll variable or this array, and then we basically write those to the yaw pitch roll data struct, right? And here's the quat to Euler sort of function. And then there's things like get a moving average world X acceleration. So we have like a moving average kind of function here. Yeah, I don't know how much we use this, but yeah, so that's handle run nav. Check BTLE. So check BTLE is basically saying, let's check if there's any messages, and really there's a lot of crazy stuff going on here, but basically I'm saying, here it is. So basically my phone can send a Bluetooth message to the rocket, and we get this as a data character, and if the message is an F, and if the state that we were in is idle, and we're not in test mode, then check if the pyro continuity is equal to 1, obviously, right? We want to make sure the pyro works, and then go to the state launch commanded. If we do this, but the pyro continuity is not 1, then just go to an abort state, basically. And then here, if we're not in idle state, just ignore it. There's a few other things here that I did, that are like helper functions and things like that. So one is Z, which I was using for testing, so it would just like zero the gyros. Another one that's important is I have a button on my phone that aborts the flight. So anytime it's sent an A, we just go to the abort state, no matter what part of the flight we're in. Then there's different characters that were sent for zeroing the servos, so centering the servos, left and right. So this is like centering it +1, or sorry, +1, -1 in each direction. Then there's a thing that's reading TBC centers, which I don't think I use this in the flight. It's just for testing. Then there's start servo test. So this is a little thing where I press and my phone, and the servo sort of gimbal the motor all like in a circle all the way around, just to sort of see if there's anything catching on them. And that's it for the check BTLE. So this check BTLE stuff happens every loop. So it's just checking if we have any data in, and if we do, deal with the data. And it's mainly like during the flight, it's mainly the abort function that's really important. Then there's handle writing to flash. So all this does is it takes the data struct that we had before, and it basically writes to the flash if we have the status is true. So it writes the data to the flash chip. Handle EUI, that's another electric UI thing. So if in the config, if it's not enabled, this just doesn't do anything. Same thing as GPS. We don't have GPS enabled mostly. This is for like testing stuff. Then there's handle battery check. So in handle battery check, we check it every 50 milliseconds. We probably should do it not as often. It's not a big deal to be, we don't need to check it while it's in flight. But because we're in, this runs also when we're in idle. It's good to see on my phone sort of the battery voltage. And then here are a few sort of extra things before we get into the this switch case statement, which goes through the states. So for example, if we are not in a launch commanded state, then the pyros should all be just always stopped, right? So we should always be writing 0 to the pyro pins. So basically, most of the time we're not in a launch commanded state. Here, if we are in a launch commanded state or in a powered ascent state, then we should be looking if the angle is past, the rocket angle is past a certain safety threshold. So if the, let's say, yaw or pitch goes past 45 degrees, then we say that's unsafe, and we should go to the abort state, which will automatically turn on the parachute. So that's only being checked if we're in a launch commanded state or if we're in a powered ascent state. If we're in an unpowered ascent state, at that point the motor has burnt out, and we are fully expecting the rocket to rotate and stuff a lot of times, and so we wouldn't want this to abort the flight just yet. But while it's flying, while the rocket is actually being pushed by the rocket motor, we do not want it to keep flying if it reaches past a certain threshold. And this function basically just checks the yaw, pitch, and roll, and decides what to do. And decides if it's past the threshold or not. And we have the threshold in the config file. So next is this big chunk, which is just sort of a switch case statement on the data state variable. So just like we had data state for idle, there's launch commanded, things like that. So let's talk about, before we get into this, let's talk about the config. So the config is this file over here, which is very important, config.h, and it has all of these definitions for a bunch of these variables that are very important for flights that I customize. Sometimes I customize for different flights depending on the motor I use and things like that. So these variables right now are like ready for like a full flight. Nothing needs to be changed here except a few variables. So things like test mode or dump mode, I set that to false because we're not doing any of those for now. Enable parachute is true. Enable angle check is true. So this is if we're flying and we want to have this safety check, then yes, we need to enable the angle check. Abort angle threshold. So this is how many degrees past how many degrees you should go before the abort signal gets triggered. So if the rocket's past 30 degrees in yaw or pitch, abort the flight. This is where you can change it to whatever you want, really. Self-fire equals true. So this was the kind of thing that I was working on where if I wanted to, because right now the rocket computer has some MOSFETs that can apply the current to the rocket motor and fire the rocket by itself. It doesn't need me to hold on to a battery with a wire and a launch little button thing and have it done manually, right? So this self-fire basically says, hey, we're using the Bluetooth to fire, like Bluetooth and flight computer self-contained to fire this rocket. We're not using a separate a separate sort of ignition system that's on the ground. And I wanted to have this feature where I could use the ignition system on the ground on the ground if I needed to. But for now, for all my flights, they're all self-fired and seems to work fine. Engage pyro equals true. This is basically I turn this off if I'm testing and stuff. So basically says, hey, whenever we tell the pyro to fire, we're going to check if we are actually allowed to fire it, and then we're going to fire it. So this is just saying, okay, in this flight we need to have the pyros engaged. Then there's things like do EUI and do GPS. So actually this should be probably false for the do GPS. And basically this is for testing purposes, and this is when I did have a GPS thing attached to the rocket, but I don't use that anymore. Parachute altitude threshold. So this is basically when we are in a state of descending. So when the rocket has detected that it is falling now, this is the altitude at which the parachute should turn on, right? Should deploy. If you are, if you're flying up to 90 meters and you want, it's kind of just like a safety thing. This is very different for different rockets and different sizes or different weights. and how high you go. So, if you're flying like a smaller rocket with a smaller motor and you go up to only 30 meters, you would say, okay, this parachute altitude threshold could be 20 meters, right? You could also put this as 30 meters or 100 meters or 1,000 meters. And if you put this as 1,000 meters, the parachute will deploy right when it detects that the rocket has gone from going up to going down, right? So right when it detects that the rocket has started to fall. So, but because of wind and stuff, you usually don't want your rocket to fall right away, right? Or sorry, to deploy its parachute right away. You want the rocket to come down faster and then deploy the parachute somewhere a little bit lower down so that it doesn't drift as far. So this is a value you can change depending on your rocket and things like that. And it depends on your parachute too, and how quickly your parachute is expected to unfold. Then there's some variables for pitch over maneuvers. So I've got a sort of little function that I built extra where basically during the flight, at some time, which is the pitch over time, at some time into the flight, we start this pitch over sort of maneuver where we basically say, okay, at time, for example, 1 second, start to set the set point of either the Y or Z axes to 25, but increment it to 25. So over a span of 1 second here, so this is pitch over length, over the span of 1 second, start incrementing the set point to 25, right? And that basically, sets the set point to 25, so it makes the rocket pitch over to a certain angle. I don't really use this much because it's cool, and I do have that in one of my videos, but I like to see the rocket go high up. And the motor I have, the F-15 motors, they still just burn for only 3.5 seconds, so like it's not a very satisfying sort of thing to see, I guess. So I usually just have these disabled, so these are false. Data sample rate, so yeah, like how many times a second do you want to sample data? 200 for my system is fine. Data sample total time, so this is how many seconds, like what's the maximum number of seconds that you want to be logging data for after you've launched the rocket. 45 seconds is like lots of time, basically. Landing detect delay, so this thing is sort of like when I think it's like after we launch the parachute, because I'd like to use like timers and count some time before I go to like a landing state rather than always rely on sensors to know if I've landed. This is just a thing to say, okay, this is like after 15 seconds of the parachute being open, let's just assume it's landed, and it works fine. Like I don't need to like change this, or because like I don't really care too much about the data after the parachutes come out. Then there's abort to landed delay. I don't know what this is anymore, but this seems to work. 20 seconds. Motor fail delay. So this is how much time the rocket sort of waits before it sees. So when we press launch, the rocket, like we send a signal to the pyros to launch the rocket, but if we press launch and within 10 seconds the rocket hasn't fired, we go into like an abort state. And so this is like, within 10 seconds if it hasn't fired, then it's probably not going to fire, so we're going to go into abort state. Y and Z set points. So these are the initial set points. So I always just have it set at 0 degrees. You can. It would be cool to start them off at like 5 degrees, but then like it might just be like a big jump. But yeah, I haven't set these to anything but 0 at the very beginning. Then there's P&ID gains. So these are different gains depending on which motor I use. So these are the gains I use for an F-15. These are the gains I use for an E12 motor. And then these basically, depending on the motor I'm going to use, I feed these into the actual PIDs values here that I use for the Y and Z. So there you go. Yaw pitch bias count. This is just how many sort of samples do I take to get the bias for the yaw and pitch. Same thing, world Excel bias, gyro bias stuff. voltage minimum. So this is my sort of threshold for my battery voltage before I say, hey, this is too low. So about 11.2 volts. I usually have it fully charged before I fly. Nav rate is every 5 milliseconds. So every 5 milliseconds we do a PNID loop update and all that good stuff. These are the sort of servo values that we write to deploy the parachute or initialize the parachute. These are just written in from experimentation. Then there's telemetry rate. This is just how often do I send over telemetry packets to the phone while we're in idle, so every 20 milliseconds. And servo range, so we don't want to allow the servos to go past this plus or minus 26 whatever values. I had to like lower this because of the way the frame was built. It was bumping against the servo, but seems like it's okay. These are the initial centers that I put in for Y and Z, but these get overwritten by the whatever's in the flash. Pyro continuity threshold. So this is if the pyros are lower, the pyro analog value is lower than this, then we have no continuity. If it's higher than this, we say, okay, there's continuity. Fire on time. So this is how long we have the pyro on for. So like the current flows into the pyro igniter for 1 second, which I don't know. It could be shorter, it could be longer, but I just have it on this long and it works. Launch acceleration threshold. So this is how many meters squared per second the rocket needs to be detected to go upwards to say that we are in a powered ascent state. Then there's a Accel unpowered threshold. So when the motor burns out, once we get to, I think, below 1.5 meters per second squared on the sort of x-axis, up and down axis, then we say that we are now in an unpowered ascent stage. Then there's a fire to PID delay. So this is sort of, so I know that by like experimentation, the rocket motor takes about 300 to 400 milliseconds to actually ignite after we send it the signal. So this waits basically that much time before we start to do PID control. You could do this also by like sensing acceleration, but this, by the time we accelerate, I guess it might be a little bit late. So I don't know. This value 400 milliseconds seems to be just perfect. Then there's parachute eject safety time. I don't remember what I did use this for anymore, and it looks like it's 10 or 100 seconds. I don't know, but anyways. I don't think I use this at all, but so let's go back to the main CPP. So let's just look at some of the, I'm going to do a little whiteboarding here. So let's look at some of the phases of flight, right? So this is really important to sort of have in your mind. So the first phase of flight, which we say, hey, this is phase 1, is just idle, right? So the rocket's standing on the pad, there's the rocket, it's standing on the pad, it's just waiting for a signal, right? It's just idle. Nothing has told it to launch yet, right? We haven't told it to launch, and it'll just sit here. And so we can see in idle, this is what it does. While it's in idle, we send telemetry packets to my phone to see, if all the sensors are working fine and all that. We check the continuity of the pyros, so we constantly check the continuity. And if we want to do a servo test, this will handle the servo test. So if we send a command to do it, what we also do is if we're telling the gyros to be zeroed, then it zeroes the gyroscope. I think this is for testing. And then we say and then only in idle do we check if we're not in a self-fire state. So remember back in the config when I said, if we're not self-firing, that means that we have a manual igniter that's attached to a wire, and we have the wire going back to me, and I press the button, and it's like a ground-based igniter. And basically, in this case, because the rocket's in idle at this point, and it needs to detect. Well, it doesn't know when we've actually fired it until it detects that, hey, my acceleration's going up, so I must be in a powered ascent stage, right? And so if it goes past this launch accel threshold, then we say, okay, zero the gyroscope, zero the Kalman filter, and then go to the powered ascent stage and continue on from there and make sure the PID status is true. I've never used this before because I never launch manually, so I don't know if this is like the right, this is the best way to do it. Is by the time it's at 2 milliseconds, is it too late to be zeroing the gyroscopes? I don't know. Or sorry, 2 meters per second squared. Is it too late to zero the gyroscopes? I don't know. So I haven't used this. Handles servo centering. So this is again, if we send a command to change what the center point of the servos are, this will handle that for us while we're in idle. So next is, next phase is the launch commanded phase. So launch commanded only occurs, as you've seen in the Bluetooth section, only occurs when I press launch on my phone. The only way that it'll let me, it'll go in launch commanded state is, if my phone, because my phone's getting telemetry data all this time, and it's getting the data on the continuity. And so first off, if there's no continuity, my phone in the app, it sort of shows that there's no that I can't press the fire button. It will not let me physically press the fire button unless there's continuity. I have a little thing where I actually have to press a button to arm the pyro, and then it asks me, "Are you sure?" And then I say yes, and only then does it let me press the fire button. So I have to, there has to be continuity, and I have to accept that yes, we're arming it, and then finally I have to press the fire button. But for extra safety, even when I do press the fire button, the fire signal goes to the rocket. The rocket does a last check to see, is there continuity, and are we also in pyro enabled mode or whatever, and then it sends the signal to fire the pyros. So that's that's sort of pretty important. Is the Bluetooth connection sort of sends the fire command. And we go into this launch commanded state. So launch commanded is the second state. So we're in state 2, which is launch commanded. So the rocket's at launch commanded, the rocket is still on the pad, and we've sent it a signal to tell it to fire, right? And while it's on the pad, while it's in launch commanded, the flame from the rocket starts to come out, and at some point it starts to go up, right? So here we'll see what launch command looks like. So we basically say, okay, if this is the first time we're going through this launch commanded sort of loop, we're going to set a lot of these sort of variables and things like that, because we also want to sort of count some time for these things. And when we get to launch commanded state, we say handle fire pyro. And handle fire pyro is just saying, okay, if we have it enabled and the status is false, but the fire time is 0, we're going to start counting. This is basically, it's a bit complicated, but basically it's just so that we can fire only for that, remember that 1 second, right? So this fire on time, it makes sure that we enable the pyro only for that 1 second, and then we stop the pyro after that. So that does the handle fire pyro, and while we're counting these, while we're doing that, we're basically counting, doing this millisecond counting, and seeing, okay, should we enable the PID yet? Should we enable it yet? Should we enable it yet? And then once this time goes past this threshold of 400 milliseconds after we've pressed launch, then we're going to say, okay, PIDs are enabled. Whatever function at the top that is handling PIDs will now start actually calculating PID values and moving the servos. Here's also, we say, well, what about if the time, if we pressed launch but it's nothing happened? Then we get into this motor fail, nothing happened for 10 seconds. Then we go into an abort state. We make sure to stop the pyros. Lastly, which is the sort of happy path, is once we sense that the acceleration of the rocket has gone past 2 meters per second squared, we will go into this powered ascent stage. And at that point, we stop the pyro firing because that means the pyro has worked, right? So we get into the powered ascent stage. So that's stage number 3. So let me, how do I move? Okay, so that was 1. So then we have powered ascent stage. So this is when the rocket has just left the pad and has, it's positively going upwards at more than 2 meters per second squared. Okay? So now we're in powered ascent stage. That's stage 3 in this case. Well, I have these as like 0, 1, 2, 3, but this is stage 3 in this case. So in powered ascent, in powered ascent, we make sure the PID status is true no matter how long we waited, right? So I don't know, so just in case, right? So we want the PID status to be true so that we are doing PID sort of control. We're saying if this is the, we're also counting how long this powered ascent stage is. Here, I don't know what this did anymore. I don't really think we need it, but it'll still be there in the repo. I'm not going to change it. So as it's going up, it's doing its handling. So this is where it's actually doing the navigation, right? Because PID status is true. This is when it's doing navigation and PID control and actually controlling the rocket with that function up above. And then here we're getting the acceleration magnitudes, right? And we don't really need it, but this is just for data logging. And then here we say, okay, well, we're gonna now wait until the acceleration goes below 1.5 meters per second squared again, right? So next time it goes below that, now we are in unpowered ascent, in the unpowered ascent stage. But also, just in case, if we notice that the velocity of the rocket is going below negative 0.5 for any reason, we're just going to say, hey, this is in free descent stage, and it goes down to the free descent stage. So, but that's sort of the non-happy path. The happy path here is where, once the motor burns out, we get to this, we get below 1.5 meters per second squared, and we go into unpowered descent. So unpowered descent looks like, looks like this. So unpowered descent is when, the motor's up in the air now, and the motor has just burnt out, so there's a little puff of smoke at the end or whatever, and the ground is like way down here, and this is 4. This is really high up. There's clouds, maybe just to show that we're in clouds, and this is motor burnout. Unpowered ascent, we're not getting any more acceleration, but we're still going upwards, right? So x velocity, is going up, x acceleration is not going up at all, and then x position is still going up, right? So x position is going up. So that's unpowered ascent. And we detect that again by just seeing if we go below 1.5 meters per second squared. I don't exactly look at like 0 and stuff because I don't know. I like to do it beforehand. These values were kind of randomly, not really randomly chosen, but just like my best guesses or estimates is what works. So in unpowered ascent, we now tell the PIDs to, hey, stop worrying about calculating stuff because you can't control the rocket. So turn off, please. And then we're just waiting until we get to free descent. And this is a point where we hit the apogee, right? Or not really the apogee, but this is the point where we start to go back down. And so here we say, we're looking at the Kalman filter and we're saying, hey, once the Kalman velocity, or once the velocity of the rocket, the vertical velocity, starts to go into the negatives, which is negative 0.5, we're now in free descent, right? So if we go, so basically this state 5 is now when the rocket is hopefully not maybe pointing down or whatever, right? Or sideways or whatever. But let's say it's like this. There's the legs and stuff, and it's up in the clouds now. But now it's starting to go down, right? So x position is starting to go down, x velocity is starting to go down, and negative is starting to fall. So if you look at like a graph of sort of velocity, this is sort of what it looks like, right? So it launches, it goes up, 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 and then around this point, or this point where it starts to fall, it's in free descent mode right now. So we go into free descent, and we're just basically now looking for next time we need to launch the parachute, right? So this is where, while it's falling, we just check what is the altitude, is it below whatever our threshold was, and if it is, go into this parachute descent mode and start logging this time for detecting landing. And going into parachute descent mode, so what parachute descent mode is, let's see, once we hit, so this is state 6, once we have the rocket and let's just have it again, whoops, let's have it again just pointing up or whatever, like this. Once it passes a certain threshold of, for example, 70 meters, and it's below 70 meters, so it's below 70 meters, then we are in parachute descent mode. And at parachute descent mode, that's when the parachute pops up and, brings us down or whatever, right? Or, folds out. So in this case, this is the deploy parachute command, starts to happen on the parachute descent mode. Technically, this is like parachute descent commanded, but deploy parachute here, and this is where we say if we enabled the parachute in config, write this deploy value to the servo, and it'll pop out the parachute, right? So this will deploy it. And at this point, we're just waiting for when it lands, and the only thing we're doing to see if it's landed is just waiting a certain amount of time, right? Since we deployed the parachute, and in this case, 15 seconds after we deploy the parachute, we're assuming the rocket has landed. And in landed mode, we wait a little bit, we write the data to the SD card, and then we do a bunch of buzz completes, and we keep buzzing to let me know that the SD card transfer has been successful. Yeah, and then other than that state, there's an abort state, which is basically, we deploy the parachute during abort, and then we tell it to go into a landed state after 15 seconds, and then we save the data. And that's really it. That's all that's really happening in the rocket. There's not really too much crazy stuff, I guess. The common filter stuff, I think I talked about that in a previous video, and it's basically the same as that video. Mainly, I think the parts that I haven't talked about before have been mainly the navigation stuff, which probably would be like a whole nother video, and a lot of me like relearning how I did these things, because this is a lot of stuff that I've forgotten, and luckily it works still. But yeah, another very important thing for a custom board is that you need to have a different variant.h file for your board, right? Because if we go back to here to my repo or whatever, my profile, and we look at Cygnus X1 here. So this is my custom. This is the flight computer that runs all of this. It's the pins on this flight computer. Oh, I can't. Yeah, okay. This flight computer and all these pins are assigned to things, custom assigned to things, right? Like they specifically go to, some go to the SD card, some go to the Bluetooth, some go to the flash, and they all, the software needs to know what pins they are, right? So we have this variant.h and variant.cpp files. So I think it's in the variant. Depends on. I think it's variant CPP. So in variant CPP, this is the important stuff here. So this is important for setting what sort of function those pins should have. So a lot of these things have already been written. I've taken this from the Adafruit. I think it was from the Adafruit stuff. Yeah, this is from like the Adafruit Cortex M4 processor, the Feather. Yeah, the Feather M4. and a lot of these are already like based on the feathers pins, and so but I have specific pins that go specific places, myself, so I had to change these. So for example, I have things like pyro PWM pins. So these pins on the microcontroller, they are specific. There's specific things that you need to turn on and off for them, like different timers and stuff like that, and interrupts, and like that's all in like the data sheet. And then you set also the buzzer and NeoPixel PWM stuff, the servo PWM, analog inputs, things for roll motors. I do have like my board does have like a spot for a roll control motor, sort of on the side here. There's supposed to be a little chip. I think it's actually this chip, but the roll control motor doesn't work. I think I screwed up some wiring or whatever, and I don't use it. So yeah, so that's sort of what you need to change to tell the software like, hey, these pins are supposed to be configured in this way. Especially like SPI pins and I2C pins, because I have I2C for the altimeter, but I also have SPI pins for the Bluetooth, SD card, and flash. SPI pins just for flash, I guess, and SPI pins for Bluetooth. And then like these are some extras that I just don't use. I think these are just things that the Adafruit feather has. But then here's like I2C pins that I use for my gyroscope and accelerometer. Yeah, and that's mainly it. But I think invariant.h is where you also sort of change things. So I have here all other pins. So this is where I define the pins. So wherever you see, my code say pyro 1 pin, fire, or pyro 2 pin, or whatever, or buzzer pin, this is where you tell it what pin numbers they actually are. And these never change for me because the flight computer, the PCB is already made. So these are all just hard coded in for me. So you'd want to change these for your own thing, or I fully expect no one to be actually using this program as is, because it's very custom to my computer, my flight computer. But like I'm sure that there's definitely going to be a lot of value from seeing how certain things are done. Especially like going through the different states and how to structure the program. Even though my programming for this kind of stuff is kind of atrocious. But yeah, then there's like pins for the gyro accelerometer, SDA and SCL pins. Same for the altimeter, SPI flash pins and stuff like that, Bluetooth pins. Yeah, and that's mainly it. And like LED pins, but I don't think I use these. This is my NeoPixel pin right here, 8. Yeah, so that's mainly it. Feel free to like go in here and learn about all these other files and stuff. One library that I use that I extensively use, that's a super great library, is this Chrono Library. And Chrono is great because, like, for example, like all you need to do, so let's say like I want my navigation code to run and recalculate my PID values every 5 milliseconds. Rather than keeping track of the time every time and worrying about millis and all that stuff, I just initiate a chrono timer. So I just say chrono nav timer, and then whenever I want to use that timer, here it is, I just say, okay, whenever my timer has passed this rate, so it has passed 5 milliseconds, do this stuff, restart the timer, so set it back to 0, and then the next time it goes to, the next time it's past 5 milliseconds, it'll run this again, right? So it's super easy. You don't need to work. And this, like, there's a lot of places where I use this just to do things, based on time, and where so that I don't have to have delays. So the only places where there are delays are like either in the startup code where it's not important, or in like special modes and stuff, like test modes and stuff. So you definitely don't want to have delays happening in your actual like full full loop or whatever. Yeah, so thanks for watching. Hope you enjoyed it. Hope this was educational and you can get a lot of information out of this. And If you have any questions, ask me in the comments section here or in the Discord. You know how to do that if you're one of those people. Yeah, and I'd be happy to explain some things and stuff. My next sort of launch that I'm gonna hopefully try to do this month is a dual stage, two-stage launch, and we'll see. I'll try to have a video out on that when it happens. The dual stage launch, I don't think it'll be very successful, but this is kind of like a last hurrah before I run out of rocket motors, and I don't want to deal with it. So yeah, thanks for watching. See you next time.